Okay, in the last video we looked at the determinant of a matrix A, and we found that that had it was a singular matrix, which is a special case where the determinant is equal to 0. Now when we come on to do the inversion of matrices, one of the problems that engineers have when they are looking at structures, analysing structures using matrices, is where a matrix is singular or close to singular. So sometimes if you don't set up your structural model very well, so you have large elements next to small elements, for example, you can get situations where you get what are called poorly conditioned matrices, where they are close to being singular, and that gives the computers problems when it comes to inverting the matrices. So we're going to look at a slightly different matrix: 4, 5, 6, 7, 8, and then instead of these being multiples of 3, we'll make this last one 10, and we will carry out the determinant, or calculate the determinant of that matrix A. Okay. So if we work through the cofactors, the cofactor matrix, so we'll start with the cofactor of this, and if you remember, it's plus minus plus minus plus minus plus minus plus, so they alternate. So we've got a plus, and then we take the determinant of the minor, which for this one is, we eliminate this row and this column, and we're left with det 5, 6, 8, 10, and that is the determinant, that is the cofactor which ends up in here. So that is equal to plus, and then that's 5 tens are 50, minus 6 eights are 48, so that's plus 2. Okay. For this location, the cofactor is minus the determinant of the minor, so we eliminate this column and this row, so we get 4, 6, 7, 10, so that's 40, so minus 40, minus 6 sevens are 42, so that is minus minus 2, which is again plus 2. Okay. Similarly, we are plus the determinants for this location here. We have the determinant of 4, 5, 7, 8. 4 eighths are 32, so we're plus 32, so it's plus from here. So we get this plus minus plus, plus minus plus. So 32 minus 7 fives are 35. So this is minus 3. Plus minus 3 is minus 3. The next one here is minus the determinant of 2, 3, 8, 10. So 2 10s are 20, minus 3 8s are 24. So I've got minus 4, which is plus 4. Where did we do that for? 2, 3, 8, 10. Yes, so that's correct. Plus 4. The next one here is plus, and we have 1, 3, 7, 10. So that gives us 110 is, so we've got plus 10 minus 21. 10 minus 21 is minus 11, plus minus 11 is minus 11. Okay, this one here is minus the determinant of 1, 2, 7, 8. Which gives us minus 1, 8 is 8. 2 7s are 14. 8 minus 14 is minus 6. Minus 6 is plus 6. Okay. 7. So for this spot here, we are plus the determinant of 2, 3, 5, 6. 2 6s are 12. Minus 3 5s are 15. 12 minus 15 is minus 3, plus minus 3 is minus 3. This one here is minus the determinant of 1, 3, 4, 6. Which is minus 1, 6 is 6. Minus 3 4s are 12. Which is minus 6, which is plus 6. And lastly, this one down here is plus, and we have 1, 2, 4, 5. 1 5, so this is plus. 1 5 is 5. 2 4s are 8. 5 minus 8 is minus 3, plus minus 3 is minus 3. Now, the next thing we're going to, or the next concept we're going to introduce is something called the adjoint of A. And the adjoint of A is equal to the transpose of our cofactors matrix. Okay, so the matrix of cofactors we've calculated here, and if we transpose that, then we get something which is called the adjoint of A, and that will be something that we come to use in working out the inverse of A. So the next thing then to do is to transpose this, so we end up with this row becoming the first row becoming the first column. So 2, 2 minus 3. The second row, 4 minus 11, 6. And then the last row becoming the last column, minus 3, 6, minus 3. So that is something which we call the transpose of the cofactors, the matrix of cofactors of A, which is equal to the same thing as, by definition almost, the adjoint of A. Okay. Now that we have the adjoint of A, if I make a bit of room, so if we just get rid of all these calculations that we were doing, we can now come on to calculate the inverse of the matrix A, which is what we need to use. The last thing that we need before we invert our matrix then is to calculate the determinant of A. So A, or the determinant of A, I think we've called it det A in the past, which can be written as this, which again is equal to the determinant of the 1, 2, 3, 4, 5, 6, 7, 8, and this time 10. We had 9 in the previous example when we worked out the determinant, but because that was a singular matrix, the 9 being a factor of these having a common factor meant that the determinant was equal to 0. Now we should get a non-zero determinant, and the non-zero determinant, we can, if you were following through what we were doing to determine the cofactors, we can just take the cofactors for one of these rows, or indeed one of these columns, and get the determinant. So 1 times 2, so this times its cofactor, plus 2 times 2, plus 3 times minus 3, will give us our determinant, which is equal to 1 times 2 is 2, plus 2 2s are 4, plus 3 times minus 3 is minus 9. So 2 plus 4 is 6 minus 9, so the determinant of that is minus 3. And you could do that using any of these rows. So we use this row 1, 2, 3, and 2, 2, and minus 3. But you could do it with 4, 5, 6, and 4, minus 11, and 6, or you could do it with 7, 8, 10, minus 3, 6, and minus 3. 1, 4, 7, 2, 4, minus 3. These would all give you the same value, if you've done it right, of minus 3, and that is a way of checking it possibly. But hopefully if you take any of these rows or columns and multiply by the cofactors, then you will get the determinant, if you've been following the maths in the previous video sessions. Okay, so in order to work out the inverse of the matrix, then we take the adjoint of the matrix A, so this one here, and then the inverse is given by the adjoint matrix divided by the determinant. And that's why we had to change this 9 to a 10, because if you divide by a determinant that's 0, then you get infinite. You know, it's a non-soluble or non-invertible matrix. And that's what I was talking about. Sometimes you get something that are close to singular, so that you get a poorly conditioned matrix, and the computer can't invert the matrix, or if it does invert the matrix, but errors creep in. So that's something that we as engineers have to watch out for when we're modelling structures. So we've got this one which has a non-zero determinant, so we can go through and take our adjoint matrix and divide through each of those by the determinant. So this is det A. So our a to the -1 now then is equal to 1 over -3 multiplied by our transpose of the cofactors, or the adjoint of A. So that's 2, 4, -3, 2 minus 11, 6, -3, 6, -3. Okay. And that is our, we can actually take that through if we want to work out the actual values. So a to the -1 is 2 over -3, 4 over -3, -3 over -3, 2 over -3, -11 over -3, 6 over -3, -3 over -3, 6 over -3, -3 over -3. So this is our, oops, daisy. Sorry. That is our inverted matrix.